What we'll do finally then is run through, so we've gone through a forced entry regression there, and we'll run through a hierarchical regression now. And this was the second part of your practical. And we'll skip stepwise regression. So we'll have covered stepwise regression in your lecture. And generally, most of the time you'd avoid using stepwise regression. You'd use either a forced entry method or hierarchical regression. And the hierarchical regression is widely used when you've got some variables that, say, you want to control for, maybe sort of demographic variables. So you'd want to control for those in the first step and then have a look at the effect of additional variables. Or quite often what you'll have is data where you know from past research that some variables predict some kind of outcome. But what you want to do is look at the effects of additional variables after, again, you've controlled for those original variables. So an example, we'll go back to this data set here. An example here would be, imagine you knew from past research that the amount of pay someone earns and the amount of holidays taken is significantly predictive of productivity. So you know that already, and what you want to do is see, in addition to those, whether an additional variable, cake, the amount of cake given out at work, is that also a significant contributor to the model in terms of does it also predict productivity? And I think if we run through an example of this, hopefully it will become a little bit more obvious what this is doing. So if we go up to the Analyze menu again and go down to Regression and Linear, then we get the linear regression box again. And we're putting productivity again in the dependent box. Now this time, as I said, we know from past research that pay and holidays is associated with productivity. So we're entering these variables into the first step in the model. And what we're doing in a hierarchical regression, we're basically conducting two separate regression models. The model 1, where we're using pay and holidays, so you can put those in there. And then we're conducting a separate or an additional linear regression looking at the effects of this extra variable. We do this by clicking now at this point on this next box, and you'll see it says block 2 of 2. So it's taken us to the next step. What we can do here is put cake into this box, and then it will perform two separate regression models, which when we pull up the output, will run through how to interpret this. So you can click on OK and get the output up. So then we can have a look at the output we get then for a hierarchical regression. And the first thing to notice is it's split this model summary table now into two models. So this is just split according to how you entered the variables into SPSS. So model 1, down below here, it just has the predictors, which was holidays and pay. So the combination of holidays and pay. And that model 1 just represents those predictors. Model 2 is now the model with holidays, pay, and also cake in the model as well. And the R-square statistic for model 1 was 0.299, so nearly 30% of the variance in the outcome was accounted for by the combination of holidays and pay. And you can have a look into the second box, the ANOVA table, and this gives you whether this was a significant proportion of variance. So was this a significant model over the baseline model? Model 2 you can then have a look at, and then model 2 was a combination of all three variables, and this model accounted for 37.4% of the variance in productivity. So a higher proportion of the variance than model 1, and that's always going to be the case because, as I said in the last video, the more variables you add, the more it will contribute. Even if it's only small, it will still contribute to the model in some way. And the ANOVA table for the second model indicates that model 2 is also significant at less than 0.001. So one word of warning at this stage is this model 2 for the ANOVA table. At the moment, this is comparing model 2 with all the predictor variables. It's comparing that with the baseline model. It's not comparing it with model 1. And that's really what we want. We want to see whether model 2 is an improvement on model 1. Or in other words, after including holidays and pay in the first step, does the addition of this extra variable cake, does that add significantly to the model? So what we do here is we use this row of data, and these are what's known as the change statistics. And this is one of the options we selected in SPSS to get these, where we selected R-square change. And the R-square change gives you the proportion of variance that the new model explains over the first model. So the proportion of variance attributed to the cake variable. In the column, then, you can see that the R-square change statistic was 0.075. So what that means is the cake variable is accounting for an additional 7.5% of variance in the outcome, even after having controlled for holidays and pay in step 1. And if you read along that line, you can see that you also get a p-value for this. And the p-value is 0.032, which indicates that this extra 7.5% of variance explained by model 2 is also significant. So that's what we're looking for when in step 2, is this extra variable making a significant contribution to this model. It could be the case that it adds a little bit of variance explained, but this doesn't reach significance. In this case, there's no real point in adding that extra variable to the model. And then a quick look at the coefficients table then. So you'll see this is also split now into model 1 and model 2. We'll just focus on the beta coefficients this time. And you can see that both pay and holidays in step 1 had fairly large beta coefficients, and they were both significant predictors in the model. But when you look at model 2, you can see that with the addition of this new cake variable, pay and cake are now significant predictors, but holidays isn't a significant predictor anymore. So that might seem a bit odd that it could be significant in step 1, but then not significant in step 2. What's happened here is that holidays and cake were correlated in the model. And I said that we want to avoid this as much as possible. They weren't a serious cause for concern, but what's happened is that because holidays and cake were associated, and they were also both associated with productivity, but actually cake had a stronger relationship to productivity than holidays. Essentially, this new cake variable is a better predictor of productivity, and it's sucking up a lot of the variance in productivity, which means that holidays now accounts for far less of the variance. So this can happen when you've got associated predictor variables in your model. It can really quite drastically affect the coefficients that are calculated. And the key thing for a hierarchical regression is just making careful decisions about the variables that you enter into the model and the order in which they're entered as well, because this can affect the output. So you need to make careful decisions about what variables you enter. But just to finish off, just to say, in a hierarchical regression, we've looked at a two-step model there, and we've entered 2 variables in the first step and an additional variable in second. But you're not limited to those options. You could have more than 2 steps, and you can enter more than 1 variable at a time in whatever block that you're entering. It all depends really what you want to do and get out of the data. But the options are there to go to use a 3rd step if you wanted to, And there's a balance really to be made between exploring the minutiae of the data, but also keeping things relatively simple. Not giving yourself too much of a hard time in terms of how to analyze this. But we'll finish off there for today. So that was multiple regression that we've covered. Next week, we'll go on to t-tests and ANOVAs. And there, rather than looking at associations between continuous variables, we start looking at group differences then. But the statistical concepts and the techniques are pretty much the same as what we've been covering in the regression model. Only we start using slightly different terminology, and we're usually just looking in the context of an ANOVA. So we'll go on to that next week then.